Okay, so we have an important reaction, okay, and we know that CO2 plus water is going to make H2CO3. That's carbonic acid. We've talked about CO2 acting as a Lewis acid, okay, and it does that. This, of course, is going to give off a proton and become the bicarbine, or the hydrogen carbonate. In older standards that we always learn that to be the bicarbine. All right, now this bicarbine, just going to rewrite it here, HCO3 negative, okay, can act as an acid or a base. It can go either way, but in the presence of hydroxides, okay, we know that that's going to rip the H away and produce the carbonates. Now carbonates being -2, hey, they can hook up with ions in the water, particularly the calcium ions that exist, and of course that's going to make your calcium carbonate, which is your chalk, and that's what's made in your rock sediments. Okay, now this is a driven reaction here, okay, but you should know clearly that if I add more of this, okay, as I said before, or that diagram showed, okay, if I add more CO2 hits the water, okay, we know that we're producing more H pluses, and that can react with these hydroxides, okay, and neutralize them. You know, and so taking that away, taking these hydroxides away, okay, I think this reaction can go in the reverse by Le Chatelier's principle, or slow it down, all right? So any case, really important carbon cycles that we can push these back. And of course, these guys can go in a direction, okay? And as I talked about, this right here is a buffer in our blood, but an important carbon cycle where the carbon CO2 in the air hits our oceans and can become locked into these precipitates, but these precipitates can break apart into the aqueous ions, given, okay, taking away some of these components, okay, and drive it back the other way. So as we add more acid, okay, obviously the calcium carbonate itself can be dissolved, and we saw this. Now, whether it was sodium carbonate, it's washing soda, or sodium hydrogen carbonate, baking powder, add that to hydrochloric acid, the H pluses, okay, that we attack onto the carbonate or the hydrogen carbonate will destabilize this, okay, into CO2 and water. CO2 is a very stable compound. You need to know that carbonates are susceptible, okay, into breaking back into CO2 and water. And we saw that, okay? We saw that with the lab where we actually made salt and we drove off the CO2. So this back and forth is an important part of our chemistry, all right? Whether it's the water, the air, or our blood, okay? Obviously the blood we're not making the calcium carbonate. But you have to know that the carbonate or CO2, whether you go one way or the other, is important. So very simply, what you have to know is CO2 and water makes carbonic acid, okay? And carbonic acid, okay, in the presence of an acidic solution can go backwards. That's important, all right? So why is that? Well, we have CO2, very stable compound. Why is it stable? Double bonds here, add to the stability. And as I talked about before, these oxygens pull these electrons away, so exposes this as a positive. We call a nucleophile in organic chemistry. Hey, water with its lone pairs will attack that positive, okay, push that bond off, okay, and what you've got is a carbon double bonded to an O, single bonded to an O, push that bond away. Remember, bases, this is acting as a what? A base acting as an acid. Lone pair what? Lone pair donator, lone pair acceptor. Okay, Lewis definition. And of course I've got this what? OH here. This is now going to be positive. I have one more proton than electrons. This is going to be negative here. We think the electron moves over, or the proton moves over to relieve that. And lo and behold, we have our bicarbonate. I'm sorry, our carbonic acid. If we put this in acid, this will go the other way into CO2 and water. So it can go back and forth. All right? This is not very stable. This is an unstable molecule. This is very stable, the CO2. It's the oxidized form of carbon. All right? So these are important reactions you should be aware of. And we're going to take advantage of them. Okay? So what are we going to do in this lab? Well, we're going to do and figure out how much of that what? Calcium carbonate we have. So what we're going to do is we're going to take 2 tablets. Oh, I can't stand this thing. This is gone. Was I close?
No.
Darn it. Feel bad now, I'm over. That was my last black marker. Oh. See what we got here. Give me a winner. Ah, it's so nice. Oh, it was nice. Oh, come on, come on. So 2 tabs. I'm not going to say tablets. I'm going to be edgy. Okay, tabs, right? You got a tattoo, it's tab. I think you shorten things up when you're edgy. I think if you're talking about being edgy, you're probably not edgy, okay? Was that funny? You know I'm edgy. Look at these edges. All right, so I have 2 tabs. Now we know that, oh, that's terrible. I can't even wait for you to, that was, oh, something happened. Was it close?
Yeah,
You like hit the rim.
All right. So you have 2 tabs. Come on. Oh, yeah. Okay. 2 tabs. Now each tab is 750 milligrams. We'll just say 0.75 grams. Okay, not loving life here. Better come back. So 0.75 grams. Okay, I think that's equal to what? That's equal to me throwing this again. Okay, that was farther away. So we've got what? 1.0 starts out good, grams of calcium carbonate. Hey, that's our drug. Okay, and that's what we're going to titrate. Now, in truth, okay, what are we really titrating? Not the calcium. Okay, that's not going to work. It's flat now. Okay, what we're titrating, party people, is CO3 -2. Okay? And what do we know? This thing is going to absorb how many what? How many H pluses? Good job. 2 H pluses, right? Yeah.
Okay, it's okay.
I'm really getting frustrated here.
So,
Oh.
deep breaths.
Okay. So this is going to absorb 2. Not having fun. All right. So we have to understand that there is, just because it's -2, it's absorbing 2 H pluses. All right. So we need to figure out how many moles of my active ingredient. Okay. So I'm going to take 1.50. Don't let me down. You'll be in the trash can. Grams.
Or at least near it.
Oh, what are you talking about? That's so funny. Calcium. I'm writing really. I want you to survive. I do. 1.50 grams of calcium carbonate. We're going to need to find how many what? Yeah. Okay. Huh. So get rid of grams. Oh, it starts off so good. 1 mole. Anyone know how many grams calcium carbonate is?
100.
Yes! You've been to the molecular mass party. And back. You survived it. Okay? What?
Not you.
So we divide by 100. Started out so good, little guy. All right. So what's my grams here? Dividing by 100 is tough. 0.0 what? 0.0150 moles of what? Calcium carbonate. But what I should do though, because it's not really about the calcium carbonate, is it? What's it about? It's about me finding a freaking marker that works! Ah!
Oh, that could have been really bad.
How do they sell these things?
That's broke. It's like shattered.
Dr. Sir.
All right, we're not getting anywhere fast today. Please don't trip and fall. All right, I do have a new shipment that came in. All right. Shit, I think I went through that shipment. All right. Okay, I'm just gonna put that box there. If this doesn't work, then I'm just gonna call it quits.
Don't mind.
Tie my shoelaces. For every one, very good. It's better. Not in love, but it's better. For every one calcium carbonate, how many H pluses will be neutralized? Good. Ooh, okay, yeah. So much better. It feels better? Yes, it flows. Okay, so this guy goes here. 3 times it by 2. So we have, what's that number? Is it 0.03 moles of H pluses? Yes, that amount of 2 tablets of that will produce. Makes sense? Yes, yes, good job. Okay, this looks like a, alpha, looks like a protein actually. Okay, so we're going to basically neutralize 0.03 moles of H plus. Okay, so here's what we're going to do. We know that if those tablets are saying what they're saying, that those tablets, each tab has 0.75 grams or 750 extra strength milligrams. Okay, we know that we should get 0.03 moles of H pluses. I'm putting the arrow down because we're neutralizing the tabs. Notice I'm edgy. Okay, the pH is going to drop. Okay, but now the party people, we don't know if we're going to get there. So what I'm going to do, okay, and besides, the carbonate is going to be in a flavor, going to be in a color, it's going to be in a binder, it's going to be hidden. It's not going to be just sitting out there in a dust for us. So we're going to crush those tablets with a mortar and pestle into a powder. And then I want to add not just exactly 0.03. The whole purpose of the lab is to figure out if our tablets are exactly 750 milligrams. I don't know if they are, so I can't build a titration based on exactly what the value is, because what if it's over and under? So what I'm going to do is I'm going to overshoot this titration. I want to add, I'm making this up, 0.04 moles of H plus. I want to over titrate. Oh my gosh, I'm going to drive the reaction to completion by adding an excess chemical. We haven't seen that before, have we, Tor? Exactly. Okay. Now, so we're going to go and overshoot it with 0.04 moles of H plus. And then here is the kicker. Okay? So I'm going to make it what? Completely fizz out by adding protons from a strong acid to the weak base and adding more H pluses than I probably have. Remember, this is an estimate. We don't know if it's going to come out this way. I'm going to overshoot it. It's going to fizz. And we're going to keep adding and stirring, and it's going to fizz, and the fizzing should stop because we should find every little tiny carbonate ion who's hiding from us. And we're going to drive the reaction by completion, Le Chatelier's principle. But then we're gonna left with a, what? A beaker that's a little acidic. And here's the cool part. We're gonna do a back titration. We're gonna go backwards with OH minus. So we're gonna add excess acid. Now we're gonna know exactly how much acid that we added. That has to be known, that we've added 0.04 moles. I'm making that number up. We can decide 0.05, 0.035, but I'm saying 0.04 is safe, depending if there's what? More or less, okay, more or less of calcium carbonate in our tabs. Remember, this is not a controlled substance. They'll say it on the tablets, and we're gonna find out that there's a lot of variability in that number when you guys do this. Okay, they don't spend thousands of dollars making sure every tablet's perfect. If they did, Tums would be an expensive drug. Expensive tablet. Okay. All right. So we're going to add excess what? Acid. Now, how much excess acid will there be? We don't know for sure. If it's perfectly 750, it'll be perfectly 0.01, right? But we don't know because the tablets may not be neutralized at this point because they may not be 750 milligrams. So we have to have some wiggle room. So we're going to add excess acid, and then we're going to back titrate the excess acid to figure out, okay, how much base was needed to figure out exactly how much excess acid. And by figuring out the excess acid, okay, I'm going to subtract that from the total amount of acid, then I'm going to know exactly where this arrow is. And that's how we're going to solve it. And I want to stop there. So we're going to design this from scratch, okay? Found a box that worked, and I let McKenna hold the rest of them, all right? So we're going to stop here, have an unbelievable time off, okay? And hopefully I see you back here Monday. If you don't see me Monday or Tuesday, because I'm moving, and we'll have a nasty sub here to tell you to sit down, put your phones away, and all that good stuff.
Do this